All right, young scientists, this should be our last screencast for Unit 6 about acids and bases, even though this one's not specifically about acids and bases. You'll notice this isn't the end of the PowerPoint presentation. It's just that everything beyond this point is review and practice of things that you've already learned. So our last topic here is going to be the solubility product. We're just tagging this in here with acids and bases because it's more equilibrium stuff, and you should be fairly confident on equilibrium at this point. Solubility is actually an equilibrium position, just like everything else everywhere is really equilibrium. Now, I'm sorry that there's even more K's, but for what we call the solubility product, because we're multiplying stuff, we have KSP. It's really just an equilibrium K again. You'll notice there's no denominator this time, though, because if we're just talking about something dissolving, our reactants are solids, and solids don't have concentrations. This makes it much simpler to calculate than typical acid-base equilibria or just general equilibria, because all we have to care about is the products. Now, remember, temperature will affect solubility. As you heat something up, generally it becomes more soluble. So our KSPs are usually at STP, they're usually at 25 degrees Celsius. And make sure that we're doing all of our concentrations in molarity, moles per liter, like we always do. So here's the KSP for this solid. I want you to find, when we say calculate the solubility, what I'm saying is what is the maximum concentration that these ions can have, which is just what your KSP calculation is going to come out with. So remember, when you go about doing this, there are two IO3 minuses in this, so the concentration will be twice as much as the copper. Set it up. You might want to draw a little ice table. Once you do that, you're going to realize this is actually pretty straightforward. Go ahead and give that a shot. Pause the video. When you're done, you can go on to the next thing. Okay, the common ion effect is just Le Chatelier's principle again. If we already have some of the ions in solution, when you add to a side, it goes to the other side. If I already have some ions, that's going to limit the solubility. That just means that you're going to add that concentration in your initial part of your ice table. It's going to decrease the solubility as a result. If you have an x cubed term with a plus and a minus, then things get a little fuzzy. You might have to approximate a little bit. Don't worry about that too much. It's not going to be that big of a deal. So here's another very similar problem. We want to calculate the solubility of CaF2, so the concentrations of calcium and fluorine. Here is their KSP, but we're putting it in a solution of 0.025 molar NaF. So the starting concentration of NaF is 0.025 molar, or really F minus is 0.025 molar. So set up your ice table, do your calculations, find the equilibrium or the maximum concentrations of calcium and fluorine. Okay, for a precipitation reaction, you'll talk about those way back in Chem 1. We can figure out if we're going to form a precipitate based on a little bit of math. Remember, we talked about Q being the reaction quotient, that quotient because we're dividing, even though in this case we're not really. If Q is less than KSP, so if the amount of ions that we mix together doesn't give us a product that's big enough, then we don't make a solid. If we don't have too many ions, then the ions don't fall out. Usually you'll find the initial concentrations of the ions. Make sure that when you find those concentrations, though, you're putting the total volume together because we're mixing two liquids. You'll plug into that normal KSP expression and just look at Q, your answer. If Q is less than KSP, no solid forms. If Q is greater than KSP, then a solid will form. So you guessed it. I'm going to have you practice that as well. We have a solution of 750 milliliters of 0.004 molar CeNO32, and we're going to add 300 milliliters of 0.02 molar KiO3. And all I want to know is, will CeIO33 precipitate? Here's your KSP. So use these concentrations and the volumes to find the moles of each. divide by the total volume to find the concentrations, and then find Q, the same way you would find KSP, and compare. Go ahead, and this is going to be the last thing that we do together anyway, so when you're done with this video. Everything from this point on is review. There are lots of practice problems for you to do. If you have any questions about them, please let me know. I also tagged electrochemistry back into here because usually we'll do electrochemistry in an acid or a basic solution, but they're the same slides you've already seen, and you should hopefully already understand how those work. All right, then let me know if you have any problems. Otherwise, we're done with this unit. Good job.